PCMX by Radio Detection. This is a video going over the new PCMX by Radio Detection. Radio Detection's had the pipeline current mapper out for several years now, and this is their third generation. I think third generation PCM, and they've updated it quite a bit. What the pipeline current mapper does is it looks for shorts and holidays, any coding faults on the pipeline, and it's basically a line locator, one of their 8100, one of the best line locators they make, and it has a magnetometer boot on it to help receive very low frequencies, very low current, because what they're trying to do is emulate DC current, cathodic protection. DC current's going to be lost anytime there's a coding defect or a short, and that of course creates corrosion in the pipe. And so this is a one-man operation, super simple to run. The things they've updated from the previous version is this one has GPS. It can store all the readings inside, give you a GPS point to it. It will work with an app called PCM Manager, and you can download that on the Android Play Store, and then that will actually tie in with all the location, give you an aerial photo of everything that's on there, every reading that you've had, and you can download it easily later and look at it and graph it out. However, this is also sold with two different transmitters, and that's where it all starts. The PCM transmitter is a 25 watt or 150 watt. The 25 watt, the benefits is it's totally portable, nice and lightweight, and it has an internal rechargeable lithium-ion battery that lasts for approximately 4 hours on regular use. And so the lithium-ion battery gets away from having to use a generator or an external AC plug-in like the 150 watt needs, and it also makes it for a smaller package. Everything here is just like the big PCM transmitter. However, this only goes up to 1 amp. The big one goes up to 3 amps. But bonus, you get 8 kilohertz with this one. And so this transmitter output is on the left side over here. And when you go to hook it up, since you are using quite a bit of power with this transmitter or the 150 watt, you need a really good ground. And we have 3 sort of ground rods over here. We found some T-posts that we put in the ground. We got our regular ground rod here, a 4-foot probe. We got them jumpered together, and we've poured Gatorade on them to give you electrolytes on your ground and builds up some continuity, gets the blood flowing and also gets the current flowing. And we're going to go ahead and try to get as much output as possible out of the transmitter. So the first thing you do is you turn the unit on, and it's going to do a battery check, says battery full, and it's going to try to increase the current setting that you got here on the left side. We have 30 milliamps, and you always want to start off at the lowest setting, 30 milliamps, 60 milliamps, 100, 300, 600, all the way up to 1 amp. The whole idea is that you're trying to work yourself up slowly while watching your voltometer up here. And this is your milliamps going out. So we are set at 30 milliamps, and you can see we got 0.03 going out. So we're good, because I know that because we don't have any voltage limit lights coming on yet. So you got 20 volts, and it ranges up to 100 volts. If I turn this up suddenly all the way, you'll see we hit voltage limit real fast. We actually got an alarm going off saying we're not getting enough power from whatever we're plugged into, but we're running off batteries, but the batteries can't handle it because we don't have a good enough ground. If I turn it down to 600, you can see we're maxing out at 100 volts. And you don't want to do a survey at 100 volts, because you'll probably end up burning up a fuse, or your battery is going to go dead pretty quick. So we'll start off at 30. I'm slowly going to turn it up. I'm going to skip 60, go up to 100, and you're going to see it slowly work its way up to 100 milliamps. We're good because we don't have any lights. Go up to 300. Oh, we got a light. We got 20 volts, but we're good to go if we want to go ahead and do the survey at 300 and 600. Let's see what we get. We go probably right up to 100 volts. Yeah, so we probably don't want to stick on that. We almost got 600 out of it. If we had another bottle of Gatorade, we could probably get 600 out of it, but I don't want to leave it at that. Oh, there we got 600. Just let it sit enough and let it cook, and it will get 600. But we're going to go ahead and turn this back down, and I am going to use the handy dandy anode, sacrificial anode that's in this test station here. So luckily we have a place to ground to when you don't have a good ground. And so distribution systems have quite a few sacrificial anodes you can utilize as grounds, and we got one right there, and we're going to see what that does. And so when I hook onto that, we're going to go up to 300 milliamps. We have no lights. I can go up to 600 milliamps. And we got 20 volts, but we're getting a lot better. Oh, we hit 100 all of a sudden. Let me fool with this a little bit. Got a bad connection in there. Okay. All right, so we are at 30 milliamps going out, no voltage. If I try to go to 600, I'm not going to quite get there. It's going to end up maxing out, so we just quite can't get there. So I'm going to just leave it at 300 for the sake of this survey. But most of the time, you're going to want to try to get it all the way up to 1 amp. And so when you go out with one of these, you want to make sure you have a lot of probe rods, 3-4 foot probe rods. You're going to have to put several of them in a series, or have an anode bed to hook onto at a rectifier or some big culvert or something with a lot of surface area, because it needs it to be able to get that current to go down that pipe. This in essence is its own little rectifier. It's using AC, not DC, but it is its own little rectifier, so think of it that way. It needs a good remote earth ground bed in order to work. The other stuff that you see on here is this is over temperature light that will come on if this is gets too hot. You want to, if it's a hot day, put it under some shade tree, or put it under its little umbrella with a margarita, and it's going to stay real happy that way. And then over on the right side, you have your frequencies. So ELF stands for extra low frequency, and what that is 98 hertz. And if all you're doing is going out and taking some current measurements and wanting to locate the pipe on a real low frequency, that would be the one to use. The next one is ELCD. It's still low frequency, 98 hertz, but it adds the current direction feature to this. So this is putting out 4 hertz, 8 hertz, 98 hertz simultaneously, not only to locate the line and give you a current measurement, but it gives you current direction to let you know which way your current's headed back to the transmitter. Your current should always be pointing from where the current's coming from on a PCM. And if you're underneath some overhead power lines, like out there in the distance, we have some overhead power lines, and you can see them right there. So if this pipe was running under those power lines parallel to it, we're possibly going to get 60 hertz influence. And 98 hertz is really close to 60 hertz. So what we do in that case is switch it over to use 512 hertz instead of 98 hertz. And the last one here after LFCD is 8 kilohertz. 8 kilohertz is a normal locate frequency. You're not going to utilize it for doing pipeline current mapping, but you can use it for a regular everyday line locator. So 8 kilohertz is found on the 7100, 8100 series locator, and since this is virtually an 8100 series receiver, it's in there as well. So if you just need a really good transmitter that will locate pipe deep and a good enough distance, 8 kilohertz works great at depths of 50 foot or even more. Utilizing 8 kilohertz with this kind of output, you should be able to locate the pipe for quite a ways. So I'm going to go ahead and go back to the ELCD mode. I'm turn this back off, go over to ELCD mode. That's the one I use 95% of the time because ELCD is your extra low frequency with current direction added to it, and you can utilize that with the A-frame too, which we'll show you in just a little bit. But I'm going to keep it on ELCD, see what my output current is. It was already saying 300, so I'm going to get out on this pipe and measure it with the receiver. So the receiver has a removable boot. When it's removed, it's an 8100 series locator. When you have the boot on, you're pipeline current mapper. And so if you go out and take a bunch of readings with the pipeline current mapper and somebody wants to borrow your locator, just give them the receiver without the boot on it, and you should be good for your storage if you've stored any readings inside the unit. But that also, if you're just going to use this as a locator, lightens the load as well, and so you're not swinging that boot around. But even though this isn't very heavy at all, it's only about a half a pound. So when you have the boot in, it's a full line pipeline current mapper, has all 5 different antennas in it, just like an 8100 series locator. You have all your different frequencies down on the bottom left hand corner, and we're already on extra low with current direction. But if I turn the frequency here, or change the frequency by hitting the F key, you'll see there's LFCD and 8 kilohertz power mode. CPS for cathodic protection system. If there's a rectified current on this pipe, we can locate it just using CPS. ELF for extra low frequency for just locating, and then back to ELCD. And so we're on ELCD. You just want to match it up to whatever the transmitter's pushing out. And let me get out here just a little ways. Get away from my hookup, get away from my ground bed, and try to get a good reading here. So I am on peak null combined mode right now, and peak null combined mode is this spider looking icon that has 4 legs. So it's a half a spider. But anyway, what on peak and null combined mode, you have arrows tell you left and right, and then you also have your peak response, which is your bar graph up on top to tell you where you got your highest response when you're over the line. And when I'm over the line, I got a compass too to tell me or orientate me the correct positioning there. I got my depth reading over here in the bottom right, and I have a current measurement over in the bottom left. Now the current measurement over here is just measuring the amount of locate current you're picking up right now. To truly take a 4 hertz current measurement, you want to push on this little milliamp button right there. And when I do that, it gives me my milliamps right there, gives me my current direction right there, and my arrow should be pointing back just like it is to the transmitter. And it's asking me, hey buddy, you want to save this reading, or do you want to just delete it and go on? So if we're not worried about saving it, I'd hit this little X, which is also your down arrow. But if I want to save it, I'd hit the check mark, and it says okay. That's the number 175. It's also trying to Bluetooth it over to my phone to save it on the PCM Manager app. And we can go ahead and follow that along if you wanted to. There is a RAM mount that radio detection makes that makes the phone sit right here next to the receiver, and you can view it on your phone as you're moving along, and you can send it on to yourself or email it to your friends and buddies, your wife. I'm sure she's interested. So I'm going to go ahead and save this reading now that I know I'm over the line by hitting the check mark there, and this is reading number 194, and that Bluetooth icon is saying, hey, I'm sending this over to my app, the RD Manager app, which Brent is running on the screen over here. You can see on the app you have a graph. Whoops, sorry, hit it accidentally. You have a chart view, which we're on right now, but then you have a map view showing you where you took your readings, and you can zoom into that and you can see where all your readings are. And then you also have a list view, and so the list view is telling me I've taken 2 readings. It's telling me exactly what those readings were, and we can kind of keep track of that as we go along. And then once we're done, I'd hit finish survey, and we'd have it all charted out, everything saved on the phone, and then easily sent to an email address or somebody else's computer, so you can do your different evaluation. So let me take a couple more readings here. And you'll hear when I hit the survey button here, you'll hear his phone go off when I save it. Just like that. So take one more here. Now what we're doing right now is called a current attenuation survey. So we are looking at the current, seeing where it drops off, and able to kind of single out where we're losing current at. As I move along, I'm just going to try to stay at the same intervals all the time. You want to use that reading right there as a benchmark on how many milliamps you were picking up. So we were right at about 100 milliamps to begin with. Normally we're going to be using 1 full amp to get going, but since we're not able to get up to that because we don't bring enough ground rods and Gatorade, we're just at 300 milliamps. But we're at 100 there. I walk, say 50 feet, take another reading, and you're just looking for current depressing. At the beginning, you're going to see maybe your current go up a little bit because you're getting out of that magnetic field of the ground rod and at the start. And so now we are at 120. What we're looking for is probably a 20-25% loss, and then it stay lost. You might have a time that your current goes up or it goes down, and that could just be because you're next to an anode, or you're next to maybe a casing vent or something big and metallic affecting your magnetic field. You got to keep in mind that you're locating magnetic fields, not the pipe. You're measuring a magnetic field around the pipe, but not voltage on the pipe itself. So we're measuring milliamps, not millivolts. but it's going to correlate. It's going to go down the same way. And as we come across any problem spot on this pipe, a short, a holiday, a bare spot, we're going to lose current. A short's going to take probably half of our current. A bare spot will probably take 25% or maybe even less. It just depends on how big of a spot, how big of a chunk of the coating's missing. But the whole idea is you move on, and this quickly and easily, just like you're locating the line, you can pay attention to your current measurement and move right along and try to find a problem spot. So we had about 120 right there. I'll go 50 foot, and after I walk 50 foot, take another reading. Looks like we're getting a little shallower here, and I'm going to see what we got. 144, so 135, there we go. So we're gaining just a little bit, and if I wanted to save that reading, I can just go ahead and hit the check mark right there. So that's reading number 176. At the same time that I'm taking these readings, GPS is also being taken. So I have a GPS point, and I can tell how good of a GPS signal I have by these bars over on the right side. 3 bars going up means it sees 8 to 12 satellites. 4 bars going to the right means it's probably got at least 8 satellites or more locked in. So we're getting good GPS right now. It's going to be about a meter accurate, but if you want, you can hook up an external GPS to get you down to 6-inch accuracy with this as well. So continue taking my readings, and we're still at 136. So I'm just going to continue on, and we'll just hurry up and do a bunch of this survey, see if we can find something up ahead. One quick note, when you come up on a road and it's a lot of traffic, you don't want to spend a lot of time on the road. So you can get to the middle of the road, quickly take your reading, and as you hear the traffic coming to knock you over, you want to save this reading, but you want to view it first. You can just freeze it by hitting the peak null button real quick. Get out of the road, and normally I do it faster than that, but you can see we are at 141 milliamps in the middle of the road, and then you can choose, do you want to save that, delete it, and go take it again? But I will go ahead and save it by hitting the check mark there, and we move on. We got a foreign line crossing right behind us that we just went past, and we're at 147 milliamps still, 145 milliamps still, didn't lose anything. So I think we are good. Either that or they're not tied in any longer. They have no bond strap going across. So the whole name of the game is that you are just looking for your milliamps to drop off. You're looking for your signal to go down. And so after you're done with your last reading, you go ahead and hit save. We can now tie this in Bluetooth wise to a telephone, a phone with the Android app RD Manager on it, or PCM Manager. And we can download all those readings, or you can also plug it in through the USB inside the battery compartment and to your computer running PCM Manager, and download the readings that way as well. So with the Pipeline Current Mapper, you also have a A-frame that goes with it to do a voltage gradient survey. And so the voltage gradient survey will actually see the current coming off the pipe in a vertical fashion and measure by a decibel return loss reading how much current you got leaving. So I'm going to go grab the A-frame out of the bag and plug it in. So on the A-frame, you have a green side and a red side. You got a couple rubber condoms to take off, so protects the spikes as it's in the bag, but the green always wants to be away from the transmitter. You always want the green out in front of you, red back towards the transmitter. And then I normally just hold the receiver off to the side. They have this nice holster to hang it on, but it's more comfortable for me to just go ahead and hold it. I'll plug in the A-frame using the blue cable that it came with. And as soon as I plug in the A-frame, it's ready. It's on AC voltage gradient. You don't have to hit any buttons. It sets itself up. And as you can see on the screen right now, you get an arrow. You get an arrow and a decibel return loss number. And that number, when you start off, will be a little high, and then it will go down. And then when you get about halfway to where the fault is, it will start to climb back up, and it will get higher and higher as you get closer and closer to the fault. And of course, when you pass the fault, the arrow will flip-flop, letting you know you've passed it and come back, and it will nail it right down to the inch where that problem spot is. So I'm going to pretend there's a problem here. Move right along. You push this in about every 10 feet or so. When you're doing the current attenuation survey without the A-frame, your intervals can be rather large. You can actually go every block if you wanted to try to find where you lost the current and then walk it out on that block that you lost all the current. But with the A-frame, it's more local. You already localized where the fault is, you got it down to a rough area, and then you start walking with the A-frame. You can go ahead and do a long survey with the A-frame, but it would take longer. But the whole nice thing about this whole system, it's kind of a one-man operation. It doesn't require much for setup. As you saw, we just hooked up, have a rechargeable battery, push out the current, go find the fault, hook up the A-frame, pinpoint exactly where the fault is, and once your arrow flip-flops, you go back to where it's at, and then you can pinpoint it also sideways by turning the A-frame this way, because it's looking for a point, not a line. When you have the A-frame plugged in, you can just move it back and forth, follow your arrow, and it will pinpoint exactly where the worst spot is. It's going to be like a null point over the top of the fault. And you can measure your decibel return loss by going roughly the same distance as the depth of the pipe. So if this pipe's 4 foot deep, I go about 4 foot out and take a decibel reading. And if I have an 83, that's a pretty bad fault. It's at an 81 right now. But you have to normalize your readings. So you always normalize your readings to 1 amp. And we have a chart, we can provide you an algorithm that you can put in to that RD Manager list view and apply it, because you want to normalize it so whatever, an 81 decibel reading would be different if you're putting out 2 amps versus 1 amp versus 300 milliamps, but you kind of need to know what your current is back right before you hit that fault. And so you save the current measurement reading here, normalize your decibel return loss reading to whatever that current reading is using that formula, and that will give you a nice consistent survey all the way through there. So, but if all you're concerned about is where that fault is and you quickly want to find it, this is a quick, easy way of doing it. So this runs off of a lithium-ion battery, recharges plugging it in right there, and you have your accessory port for the A-frame, accessory port for a headphone jack. Is there anything I'm leaving out that you can think of, Brent?
I think you pretty much covered it.
I covered everything?
Yeah, that's thorough.
That's pretty fast paced, but we offer free training for every product we sell. So of course we sell a pipeline current mapper, we'll come on site, we'll get you up and going and show you how everything works hands-on wise. But this is a quick, easy way of doing voltage gradient surveying, current attenuation surveying. There's obviously other ways of doing things like close interval surveys, DCVG. A lot of people compare this to DCVG. They wonder what's the advantages of DCVG over ACVG, or what's ACVG advantages over DCVG. I find DCVG more cumbersome. Of course, a bigger setup process.
Yeah, that's true. I mean,
what's your ideas?
Oh, you got to be able to go to each test station. You got to have an interrupter. You have to have a rectifier, install a rectifier with DCVG. You have ACVG, just hook up, go, and you just compare your decibel readings. The normalization process is actually pretty simple. It doesn't vary that much. It's just one line on an Excel sheet that you just drag all the way down.
We have a DCVG machine with this. We can hook it up real fast, or at least try to, and simulate what you would use on a DCVG versus this. And so let's grab it real quick. On a DCVG survey, you're utilizing the rectifiers that are already on the system, and you're interrupting them at a given speed. And so you have an on and an off, and you're waiting for that on and off to come on to cycle, and it will make your needle move and kind of point you when you do have a fault in the direction that current's going. So he's over here, and the setup process on the DCVG requires you to have nice distilled water with you, because that distilled water is going to fill up this probe. There's a copper line that's going all the way down here to the spike. Actually, it's going to some wooden pegs that go into the bottom here.
Yeah, and a lot of times you're also filling this water with calcium sulfate, but I think that we've got enough connectivity here that we'll be able to get her done. So here's the calcium sulfate that you oftentimes have to mix ahead of time. Then screw on your wood pegs.
Yeah, put water in.
Usually helps to let it soak in first a little bit. I mean, you got to get those wood pegs wet, and then it also helps to make it so they expand so they don't fall out.
Yeah, the wood pegs need a little bit of time to soak up that water, expand out, and so they stay in the bottom. But the whole purpose of the wood pegs is to give you a good ground contact, give you a good reading back up to the receiver. You got yours?
Yeah, trying to get it so I want to stay.
Try to sit down, get the water into it. This might take, we might not have enough time to get this wood peg to expand out. Sometimes it has to sit overnight. In theory, you don't have to really use wood pegs if you have copper to the ground, but that this is how it's set up. I don't know if there's
3.5 cell. Yeah, we'll do it.
Yeah, pour it on there.
Yep.
Expand! All right. Logging the information from this analog unit would require somebody to plug in numbers as you went along. They do have digital units too, but...
Now I guess I'll get it set up. Yeah, appreciate it.
You ever wear this when you're out clubbing?
Always.
Always. It's a good Halloween costume. Scare the children when they come for candy.
It's old school.
People driving by are wondering, what?
Yeah. Well.
All right. So what are you doing here? You got the dials.
Yeah. So what we have on here is, first off, I'm going to turn it on, do a battery check. We've got some battery, and then we're going to go to on and give it a go. Hi, my name is Brent with Subsurface Solutions. I'm here to show you the difference between DCVG, that's DC voltage gradient, where we're using a rectifier, and also ACVG, that's AC voltage gradient survey, where we're using the pipeline current mapper. And so, as you can see with DCVG, what I have is I have 2 half cells, and what they have is copper sulfate inside of here. You can also use water. You can use different types of probes that we have, wood probes. This is to make it as sensitive as possible. And what we do is we just get out, start at some ground. When it kind of zeroed out, we want to look for a tick. What we have out here is just basically an anode that is connected to the pipe, so that we just have an easy point of reference. So as I survey along this line, I'm going to start over the pipe, and I'm just going to keep one probe out front and another one behind, and we're going to get this down to about 0, and we're going to move ahead. Stop. We have an interruption on here. You need to have an interruption with a rectifier, and so what we have right now is for 8 seconds we have on with the rectifier, and then 2 seconds off right now. All right, so we've got a reference right here to basically on off. We have an interruption, and so I'm just going to check the difference between the two. And so as I survey along, I'm just keeping one probe out, another one forward, and we're just checking for the interruption. And here we go. I get a spike. This is all related to what the setting is for the millivolts on here. So right now I'm on the 25 volt millivolt reference, and then 50, and here's 100. And so we kind of got to do a little bit of math on this, but you could see it just changes from the interruption right here. And it's changing from roughly about 7 to 8, which since we're at 100, we have to divide that by 10. So 70 to 80. So what we have is we have roughly about a 10-15 millivolt change between the two. It's pretty weak, and we can try to pinpoint this even closer and see where it's the highest. And then technically right when we get over it, we'll see a null point. It's a point where it starts to zero out when it's right between the probe rods. So when we get to that point,
what we can do, if we want to examine actually what our loss is here in millivolts, we just measure out away. So I start with this sort of distance. Right now, I've got 20 on here, which basically out of 100 on a scale of 25 means that we have 80 millivolts. And then I go across here from this spot to this spot, and we add those up. And I've got another 15. Let's see if we have anything else going on anymore. And it's died down. So here we have about 105 millivolts that we're losing to this anode. That's the process. But what does that mean? Well, it means we're losing that many millivolts, but there's a lot more that we need to know. What we need to do when we're doing DCVG is we need to know what our millivolts is by checking with a half cell and a test station at one test station and another test station. We need to make a reference to how far away we are from those test stations and how much millivolts is lost between the two, and we have to measure our footage from those test stations. Once we know that distance and we know how much current loss there is, we can basically divide that. And that's what we get. That's how we get our percent IR. You know, a huge advantage with ACVG is we just hook up at the test station and we go. Our reference is just our milliamp reading, our current. That's always live on the screen as one of the surveys. And then when we're doing ACVG, we've got our other survey, a decibel reading, that's basically rated off of a normalization in decibels for how much current you have. It's actually pretty simple. There's a logarithmic formula, or just even to simplify it more when you're doing ACVG. Every time you lose your current and it gets cut in half, so when you go from 1 amp to 500 milliamps, you're just adding 6 decibels. If you started at 2 amps and then you lost some, then instead we're subtracting 6 decibels at 2 amps. It's a lot simpler than having to go out and hook up at every single test station. One of the other things that happens with DCVG that I've just noticed holding on to this is the wind's been getting to it here and there, and it's been making it go up and down. There's some things that it's susceptible to. We do have a lot of 60 hertz around too. That can mess with this. So DCVG, it's a process that's used and has been used for a long time. You need a rectifier, or else you have to have a portable rectifier to hook up. It's great for going some long distances. It's not near sensitive, so a lot of people like to choose it because they don't want to pick up every little detail and stuff. It's for longer surveys and it requires more people. ACVG, it pinpoints you to just really any single little holidays, and then it just measures it with a decibel return. You're usually looking for a decibel return of 80 plus, but that's all depends on your soil resistivity. Dig one up and you'll know exactly how much they're worth. So when it comes to DCVG versus ACVG, they're very much alike. They both work off gradients. The pipeline current mapper has a fixed A-frame, but there is a lot more simplicity to using ACVG than using DCVG. A lot of math on the back end, a lot of measurements.
But the A-frame's really nice and easy. You just hook up and go. You don't need to know near as much about it.
Yeah, you hook it up, it sets itself up. You got your transmitter already running on current direction frequency with A-frame, with fault find, and you follow the arrow. And you look at the decibel return loss. I mean, the most difficult part is if you're doing a large survey and you have to normalize your readings, but even that's pretty simple.
That's pretty plug and play.
Yeah,
and we're here to help you too.
Yep. So if you have any questions, feel free to give us a call, subsurfacesolutions.com. You can find us anytime on the internet and on our YouTube channel. And if you haven't subscribed, go ahead and click down below, subscribe now.